And the chi-square goodness of fit test was to test if a model of proportions matched what the claim was. And now we're going to look at when we want to compare multiple models at the same time. So we're just going to jump in with kind of an example. And so let's say you own a restaurant that serves European food, and you're doing an experiment to see if the type of music you play in the background will influence the type of food that people order. So you're a European restaurant, you serve French, Italian, and other entrees. And so you want to test, okay, if I play French music in the background, do more people order French food? If I play Italian music in the background, do more people order Italian food? And if I play nothing in the background, does that influence it either? So our null hypothesis is going to be that there is no difference in the true distributions of entrees ordered at this restaurant when no music, French music, or Italian music is played. And this specific test is called the chi-square test for homogeneity. Homogeneity basically just means sameness. And then based on that null hypothesis, your test would be that there is a difference in the true distributions of entrees ordered at the restaurant when no music, French accordion music, or Italian string music is played. Yes.
Thank you so much.
Of course. Okay. And just like with the Skittles experiment, the alternative hypothesis doesn't state that all the distributions are different. It just means that at least one of them has to be different. All right. So let's say this was your outcome. So now we have a two-way table. Our rows are the actual entrees ordered, and then our columns are our treatments. So we played no music, we played French, and we played Italian. And then each cell represents the number of entrees ordered under that circumstance, right? So what we want to do is compare this to what we would expect if there was no effect. So here's kind of the three different distributions under those three different treatments. So under no music, here's a bar graph showing how many French, how many Italian, how many other were ordered. French music and Italian music. And so there is a difference, obviously. But what we're going to test to see is it likely that that difference is just due to variability? Like these people were going to order those regardless of what type of background music was playing? Or is it likely due to the treatment? All right, so the issue that comes up, we could actually use a goodness of fit test, but we would have to do multiple goodness of fit tests because we have three treatment here, and we would end up with many tests and many p-values. This is a bad idea because anytime you run a test, there's a possibility that you've committed a type 1 error if you have evidence of the alternative hypothesis, right? So if you're running multiple tests, you're just increasing the probability that you've committed a type 1 error, which we don't want. So the problem of how to do many comparisons at once without increasing the overall probability of a type 1 error is common in statistics. and we've come up with methods for dealing with multiple comparisons, and they have 2 steps. First step, we're going to run an overall test to see if there's convincing evidence of any differences among the parameters that we want to compare. And then if there is evidence that there's some difference, we'll just go up just like we did in the goodness of fit test, and we can do a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. All right, so let's talk about how to find our expected counts here. Now, I'm going to go through what the math is, but then I'm going to show you in your calculator. You don't have to do this math by hand, really. But here's the general logic behind it. If the specific type of music that's playing has no effect on entree orders, the proportion of French entrees, for example, ordered under each music condition should be 99 out of 243. And all this is really saying is that if the music makes no difference, these 99 people, we're going to order French anyway, regardless of the type of music playing in the background, right? So that proportion should be the same regardless of the music, 99 out of 243. We would expect about 41% of people to order French, right? Well, when we compare that to, there were 84 entrees ordered when no music was playing, what we would expect is, again, this 41% of them to order French. Well, 41% of the total in the table, of 84, I don't know why that 1 is there, that is a typo, that should just be 84 times 0.4 is 34.22. So we would expect 34.22 to order French when no music is playing. And we can do that for every cell then in the table and get an expected count. And so the formula that comes up for expected count is you do row total times column total divided by table total. So row total times column total divided by table total. So 99 times 84 divided by 243, that got me the 34.22. If you did that for every cell, so again, let's say I wanted to get this expected value, we would do row total 31 times column total 75 divided by table total 243, and that gets me 9.57. If we did that for every cell in our table, we would get the expected count for each combination. Now, as I said, your calculator can do these for you, so let's practice how to do that right now. So this is a new function in our calculator, which is going to be the matrix function. You can see matrix, it's second, and then it's that x inverse button right above x squared. And that pulls up your matrix list. First thing you want to do is go over to edit, hit enter on A, and then you need to change the dimensions to be whatever the dimensions of your two-way table are without the margins. We don't want the totals, we just want the individual cells. So you want to change this to be a 3x3 matrix. And we're going to enter in all of our observed counts. So just like this, the 30, 39, 30, 11, 1, 19, 43, 35, 35. So just this portion of the table without the totals that are in the margins. So I'll give you a second for that. So this one's a little bit backwards because we're actually going to run the test in our calculator in order to get the expected counts. We're going to copy the expected counts matrix down, and then we'll go back and run the test a second time and actually interpret the results once we've verified all our conditions for the test. Let's see. Let's run through a full chi-square test for homogeneity. All right. Let's see. The Pew Research Center conducts surveys about a variety of topics in many different countries. In one survey, it wanted to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents of Australia, the United Kingdom, and the United States were asked many questions, including the following. Some people say that the following things are important for being truly, whatever your nationality is, whatever country you're in. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the responses to this question. And do these data provide convincing evidence at the alpha equals 0.05 level that the distributions of opinion about speaking English differ for residents of Australia, the UK, and the US? All right. So let's go through our state plan do conclude. And we're just going to state our hypotheses. And so really your null hypothesis just comes from the problem statement. We'll say the distributions of opinion about speaking English do not differ by country. And then your alternative hypothesis is just that they do differ by country, the distributions of opinions. About speaking English differ by country. And again, that doesn't mean that they're all different. We're comparing 3 different countries, right? So they don't all have to be different. We're just saying that at least one of them is different from the others, okay? All right, so here's where we want to check conditions. So plan. This is stated as a random sample. And then for the 10% condition, we need to check each sample. So we need to check that each sample is less than 10% of the population size. So we have 3 samples, 1,000, 1,460, and 1,003. Just multiply each one of them by 10. So we'll say the Australia population is greater than 10,000. The UK pop is greater than 14,600. And the US pop is greater than 10,030. Okay, so here's where we have to do the weird thing, right? We need to give our expected counts. And we'll just give those, in our case, in a 4x3 matrix. So let's practice doing that in our calculator. So what we want to enter into your calculator is this table without the margins, right? So now we'll go back into matrix, so second X inverse. We want to edit this, and you want it to be a 4x3 matrix. It's row by column. All right, so what do we have? 690, 1177, 702, and 250, 242, 221, 40, 28, 50, and then 20, oh no, 13. And 30. All right. So once we have that, let's quit. Let's go stat tests. You just want to run the chi-squared test. Observed is in matrix A, expected is in going to be put into B. Go ahead and calculate. Ignore that stuff for now. And what we want to do is access matrix B. So now it's a 4x3 matrix that has all of our expected counts in it. So I'll just round each one of these to 2 decimal places. So, oh boy. $741.84, 205.89, 34.07, 18.19. Column 2 is 1083.09, 300.60, 49.75, 26.56. And then the last column, there we go, 744.07, 206.51, 34.18, and finally 18.25. All right, and so I just threw that in a 4x3 matrix. Those are all greater than 5, so I'm good to go. So we're at the do step, and we've already technically run the test. But now we're just going to write down the statement. So running a chi-square test for homogeneity. Let's go back in our calculator. I'll just rerun that same test. Stat tests. There we go. So we get a chi-square test statistic of 68.57. And we get a p-value. So this is a very, very small p-value, right? It's times 10 to the negative 13 power. So when you're actually copying this down, you can do p is just approximately 0. You don't have to write down 12 zeros in a decimal. And then we do want to copy down our degrees of freedom given by the calculator. So df equals 6. And just to give you some insight to how degrees of freedom are calculated in this case, it's rows minus 1 times columns minus 1. This is not including the margins. So you would have, in this case, 3 times 2, which gives us 6 degrees of freedom. All right. Well, we interpret this just like we did with all our other significance level. You're going to compare your p-value to your alpha. In this case, do we have convincing evidence or do we fail to have convincing evidence? Yeah, this is a very small p-value, right? So all that's saying is that the differences in the distributions were unlikely to have occurred by chance. So conclude, at alpha equals 0.05, we reject H null in favor of HA. We have convincing evidence that opinions on speaking English differ by country. And this is where you would want to do a follow-up analysis because we're comparing 3 different countries in this case, and they don't all have to be different. So we would want to say, okay, what are the most extreme differences? And the way you can do that is go in and take a look at your observed counts and compare those to your expected counts. So where are the most extreme differences in observed versus expected? So for example, we observed 600 people and 690 people from Australia said that it's very important to speak English versus what was expected was 741. So that's a pretty significant difference when you compare that to the observed versus expected for the UK, which was actually pretty close, or the US, right? Which was also at least closer than what we would have expected from Australia. Let's see, where are some other large differences? I guess we can see kind of a large difference in the UK. We expected 300 to say it was somewhat important. We only got 242. So you only need to do that follow-up analysis if you're asked questions about it. But that's how you do the follow-up analysis. You just look at what are the largest differences in the observed counts versus the expected counts. Any questions about that? So that's the chi-square test for homogeneity. So there's one more test, and it's actually the same test. Mathematically, but we interpret the results a little bit differently because they come from a different form of sampling. The test for homogeneity is when you're running an experiment or you're comparing multiple samples to each other. This is called the test for independence. And we just state the hypothesis differently. So this is the test for independence. You can say the null hypothesis, and sorry, this example was, are people who are prone to sudden anger more likely to develop heart disease? In this case, we take an observational study of a random sample of 8,474 people with normal blood pressure for about 4 years. So notice that this data comes from a single random sample versus like the English language speaking question came from 3 independent random samples, right? So here we're taking a single random sample, and what we're looking for is if there's an association between multiple characteristics of these individuals in this single random sample, right? And so our null hypothesis would be there is no association between anger and heart disease. And then the alternative, what we're looking for is there is an association between anger and heart disease. So there's two ways you could state this. You could state it in terms of the association, or equivalently, I could state it in terms of independence. And then the null hypothesis would be that anger and heart status are independent. And then the alternative, what I'm looking for is that they are not independent, aka they are associated with one another. Okay? All right. Everything else about this test is the exact same. The conditions that you check are the same. The way you calculate the p-value, the chi-square test statistic is the same. But now you're just looking at a single population. So you only have one population to check the 10% condition on. Your large counts, you still need to write down that matrix. All right, so I'm not going to make us do all the full-on check condition, but I want you to run the test in your calculator for this. So this is, we took a random sample of winter visitors to Yellowstone National Park, and we asked them two questions. Do you belong to an environmental club like the Sierra Club? And what's your experience with a snowmobile? Own, rent, or never used? And then we have a two-way table that summarizes the data. Do these data provide convincing evidence of an association between environmental club status and the type of snowmobile use in the population of winter visitors to Yellowstone National Park? All right, so what I want to make my expected counts matrix. What dimensions does it have? It's 3 by 2, 3 rows, 2 columns. Excellent. So let's go ahead and fill in a 3 by 2 matrix. So I'll go second, X inverse, edit. Let's make this 3 by 2. All right, and I'll list them off for you. So we got 4, 4, 5, 2, 1, 2, 4, 9, 7, 77, 2, 7, 9, and 16. All right, so now we're ready to run the test. Stat tests, choose the chi-squared test. And it'll put our expected counts into matrix B. So if I go second X inverse, now I can access matrix B. Now I just have to copy down this 3 by 2 matrix, take it to 2 decimal places, and then clearly all the expected values are bigger than 5, so we're good. All right, so when I run this test, let's just one more time look at my p-value. There it is. That p-value is very small, right? Pretty much 0. So do we have evidence that there is an association between club status and snowmobile experiments, or do we fail to have evidence that there is an association between club status? We have evidence. So your alternative hypothesis is that you are looking for an association, right? So yeah, you have evidence that there is an association between environmental club status and snowmobile experience. The only other thing I want to mention, and then I'll get you to working on a problem set, is this can be really difficult, right? Because there's not any mathematical difference between the way you run the test, but there is a difference in the conditions you check and kind of the way you conclude these tests. So knowing when it's a chi-square test for homogeneity versus a chi-square test for independence, the best way to distinguish it is how the data were produced. If the data come from 2 or more independent random samples, or you're conducting an experiment, it's going to be a test for homogeneity. If the data come from one single random sample and you're trying to observe if there's an association between some categorical variables in that single random sample, then it's a chi-square test for independence, okay? All right. Well, listen.